Okay, so far we've seen a couple patterns with this little card structure we have here, okay? This one goes up by what each time? 3. This one goes up by 2, okay? That's the patterns we have here, talking about cards, talking about triangles. Investigation 2. Anybody heard of that word? Blaise Pascal? I think you're right. Not too many kids named Blaise in this country. Very good, Dannon. I can read too. Okay, well, he came up with this. This is really, really important in Math 12. Okay? This doesn't look that significant, but there are tons of interesting patterns with this funny little number thing. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. Let's do another pattern. Put a 1 there. Put a 1 there. What do you think this number is? Good job. What's this number? Wow. You see the pattern? Okay. Put a 1 there. Put a 1 there. What's this number? Oh, God, you guys are good. 10. 10. 5. Okay. It keeps going forever. In a lot of math classes in this district and worldwide, there's a poster of this with Blaise's picture on the side of it. That's Pascal's triangle. Do you see other patterns that are happening here? Yeah. 1, 2, 3, 4, 5. Doesn't go here though. We could go this way. 1, 2, 3, 4, 5. Okay. What's 1 and 2? 3. What's 2 and 3? Oh, that's not there. That's 1. Okay. What else do we have? What if I add up these numbers? There's 1. This is 2. Let's just hold this thought. What's this? 1, 2, and 1? What's this? Okay, what's this? 10, 14, 15. Do we see a pattern? Ah, doubling. Okay. There's, you know what, like, there's tons, okay? I'm not going to sit here all day trying to figure them out because I've forgotten most of them. Okay, row number. Sum of the numbers in the row. I actually kind of already started this one, didn't I? 8, row 5, 1, 2, 3, 4, 5, 16. Do we see what this should add up to? Yeah, it's so obvious. 32, then what? Okay. All right. There's lots. I'm just kind of, none's coming to my head right now, so I'll just move on. Investigation 3. Equilateral triangle is what kind of triangle? All sides, and because all sides are equal, all angles are equal too. Okay, that's nice to know. If you don't know that in Math 11 Foundations, you lose a lot of marks. If I take this length of 32 centimeters and I cut it in half, then each new length is how much? Yeah. Okay. So what's this length here? Yeah, because that's also an equilateral triangle, isn't it? If I cut that in half, what are these lengths? 8, 8, 8, and so on, and so on. But they didn't do the so on. What's the next thing I want to draw in here? Who's good with their visual skills? I'm putting a triangle inside the other triangle, but it's going to be upside down, right? Can you put a triangle in here upside down? There. Okay. Well, how much is each one of those sides? Do we see a pattern here? How far do you think we could go with this? Yeah, like that's probably about it, right? Okay. But would this ever end in theory? No. It's like an asymptote. You think to yourself, well, how does that line never touch this one? You know, it's like right here, it looks like they're on top of each other. But mathematically, they never do. Out to infinity and beyond, okay? These things never touch. That's a definition of an asymptote, because it's always some fractional value. Same thing with this. Sure, you can't see them, but this can keep going on forever and ever and ever, as long as you can blow it up and write in another triangle. Okay? Infinite. Anyway, we want a pattern here. We got a triangle number 1. The length of the side was 32. We already kind of answered this. The next, if we have 2 triangles, right, then this length would be 16, right? And then 8, 4, and this guy, if you could see it, would be 2. All right. Different pattern. There's the diagram number. How many triangles? Don't yell it out. Let us think if you see it. This is one triangle. How many total triangles do we have there? Don't yell it out. God, you just can't resist, can you? Who likes 5? A couple of you, several of you. Okay. There's 1, 2, 3, 4. Where's the 5th one? Yeah, you can include that one. That's the first one we had, isn't it? Okay. And who looked here? Yeah, right. Okay. How about this one? How many triangles do we have total? Don't yell it out. Write it down. Let's see if we're right. Put it in the next box. I better check so I don't make a mistake. All right. Who's got it? Hands up. Don't yell it out. Caitlin. Oh, I missed one. Yeah, it's 9. How's it 9? Okay, we got the big one. There's 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so these are all fun and games. The next one's getting hard, but do we see a pattern? What do you think it is? Is this increasing by 4? Bet you the next one's 13. Bet you the next one's 17. Okay, you might be there a while trying to figure that one out. Okay. I think this is the last one, investigation number 4. These were all positives. You can still have negatives and have a pattern. In Calgary, January the 1st, it was 8 degrees. For the next 10 days, we had a low pressure system come in, and the mean daily temperature decreased by 4 each day. So what was it day 2? It went down by 4. And then day 3 it was, and then, okay, yeah, all right, this is tough for grade 8s, but you guys, no problem, right? Down by 4 each day. You can still have negatives. Okay. We just filled in A, B, C, D, E, F, 6 different tables of different patterns, as my wife calls it. Okay? This is the first one. That was table A, and this is hard on me. I'm going to go like, this is like operating system 7. I'll get like dizzy if I keep flipping back and forth and looking at all these. Okay, that's table A. That's where they're getting these, right? So what was it? 3, 6, 9, 12, and 15, right? So let's just fill all these in first. Table B was 1, 3, 5, 7, 9. You getting this, Tanner? I don't see your hand moving. Table C, 1, 2, 4, 8, 16, 32, 64, right? D was what? 32, 16, 8, 4, and 2. Lengths of sides on the triangles. E, 1, 5, 9, 13, 17. That was any triangles. And lastly was the temperatures. 8, 4, 0, -4, -8. Okay. Excuse me. Lots of stuff going on here. Okay, complete the tables. Check. Complete the statement explaining how to find the next term in the sequence. But here's the tricky part. We can only use those two words. Okay? State the next two terms of the sequence. So the next term here can be calculated by, is it add or multiply? Yeah, they go up by 3, right? Plus 3, plus 3, plus 3. So if we add 3 or plus 3, okay, we can get these terms. So something I kind of just skipped over. This is important, sorry, so go back. The first term, we call that, instead of saying first term, T1. Okay? So looking at that table, for example, that's T1. The second term, T2, right? T3, the fourth term, the fifth term, and this is wrong. The second term is not 9, it's 6, right? Okay, the third term here is not 15, it's 9. As far as I know, this is my third time through this book. I think that's the only mistake in it. Like this whole book. That's pretty good, eh? One mistake.
Wait, mine says 6 and 9.
It does?
Yeah.
Oh, look at that. They fixed it with the printing then. Okay. I got the original copy in PDF, so that someone did catch it and they fixed it. All right, we'll forget that. Okay, so T1's the first term. So when they say T6, what are they talking about? The sixth term. What is the next one going to be? What is 15 plus 3? 18. What's the next one going to be? Okay, Dan, what's 18 plus 3? I know, this is helpful though, okay? This is our introduction to patterns. I told you, you're kind of like this lesson. It's not too bad, especially after our big factoring test yesterday. Okay, the next term can be calculated here by doing what? How do I get from 1 to 3, 5 to 7? Adding 2. What's the next one going to be? 11. What's the seventh term going to be? 13. So far, so good? All right. How do I get from 1 to 2? Well, there's two choices. I can add 1 or I can multiply it by 2. We have to see another one to know what the pattern is. How do I get from 2 to 4? Do I add 2 or multiply by 2? Either way. We're not sure yet. Now I'm sure I have to multiply by 2. It's not adding by 2. Again, as long as I'm using the word adding or multiply, I'm okay. Okay? What's the next one going to be? What's 64 times 2? What's 128 times 2? Okay. How do I get from 32 to 16? Don't yell it out. What is it, Shelby? He just said it. Okay, I know you want to say minus 16, but that doesn't work here. So yeah, I'm going to divide it by 2. That's what you want to say. Yeah, I have to use the words add or multiply, right? I have to multiply by a half. Or 0.5, whatever way you want to think of it, okay? So T6, what would the next term be? What's 2 times a half? Okay, what is 1 times a half? All right, no divide, no subtract. From 1 to 5, well, that might be add 4, it might be multiply by 5. Let's look at the next one. Now I'm pretty sure that's add 4, right? Okay, add 4. What's 17 and 4? What's that and 4? Okay. Shannon's getting bored, so whip through it a little quicker. How do I get from 8 to 4? I multiply by half. Okay, or subtract. Can I use the word subtract? Okay, I need to add, Lewis? Lewis? I need to add Lewis? Add what? Add negative 4. Okay, I can't use the word subtract. Okay, what is negative 8? If you know you go 4 degrees lower, that's minus 12, right? Negative 8 plus negative 4 is negative 12, right? Okay, negative 12, negative 16. All right, so far so good? Okay, definitions. When we add, there's a word for it. You have to know the difference here, okay? That's arithmetic sequence when you add. When you multiply, it's called a geometric sequence. Need to know. People forget that on the test, you're going to lose lots of marks, okay? There's other sequences. There's, for example, sequences of prime numbers. There's logarithmic sequences. There's something called a Fibonacci sequence. Anybody heard of this word before? But you never heard of Fibonacci before? There is Fibonacci. How do these, they're called sepals, aren't they, for a flower? They grow according to a Fibonacci sequence. Okay? This is one interpretation of a Fibonacci sequence. It's called the golden section, the golden rectangle, where, see this picture here? Each box has dimensions 1.6 times as long as it. This Fibonacci sequence, if you take it and divide it by the previous fraction or something like that, you get 1.61. Okay? In nature, it's all over the place. Fibonacci, in about the 11th or 12th century, was the first guy to see this. It actually started, I'm not a huge historian, but he actually wanted to breed rabbits. And somehow he came up with, they breed in, as far as the colors go, when they breed, it comes up with this funny number. Okay, the browns and the grays and the whites came up with this funny number. Since then, okay, is that something out of the sea, or is that blue-green cauliflower? I don't know. They both grow according to Fibonacci sequence. Okay? It's weird. A pine cone. When you count the spirals, it's always a Fibonacci number. What else? Hey, there's something. Look at these. There's a tree. Okay, we got one leaf, 2 leaves, 3 leaves, 1, 2, 3. Guess what the next thing on the tree is going to be? 5 leaves. Okay, branches grow like this. Antlers grow like this. Okay, it's weird. It's everywhere. Someone called it once God's number. Okay, a cactus. Someone thinks an egg makes this shape. Okay, where's the other weird ones I saw? The digits of your finger. Each section is exactly 1.6 longer than the one before it. Fibonacci number. It's yeah, and he's the first guy to discover it. People have looked at this for centuries, over and over again, trying to find different patterns. Where's the weird one? This is the weird one. All these pigeons are randomly, if you're not a math guy, on top of this, in this roof. That each one is 1.6 as far away as the next one. I don't know. I just saw the picture. I just thought, what? Do the pigeons really know this? Or what's going on? I don't know. Okay, that's like kind of cool. Unfortunately, we don't do research on this, investigate it, okay? That's what people do with their master's degrees at, university and stuff. That's as far as we get, as far as our curriculum goes. All we do is tell you what it is, where it is in nature. We just kind of need to kind of recognize that. Okay? That's another type of sequence. Here's the big ones. Those are the ones we're going to be using formulas with and figuring the stuff out. Okay. What's opposite to the word infinite? Finite. Okay. Look at these sets of numbers. How do you know, like back in grade 10, when you got a number like that, is that irrational or rational? Well, that's my question. Does it have 3 dots on the end of it? Then it terminated. It's rational. That's not pi. That is. Okay? It keeps going forever and ever and ever. If it has dots, it's infinite. If it stops, there's no dots, or there's 1 dot, period. It stops, it's finite. Okay? Got to remember that. Okay, let's just plot 2 of these. We're not going to plot them all. Just look at table A again. And it was on the top 1, 2, 3, 4, 5. The numbers in the bottom were 3, 6, 9, 12, 15, right? So 1 was 3, 2 was 6, 3 was 9, 4 was 12, 5 was 15. And does that look linear? If you remember from grade 10, if it's consistent, if you add by the same amount each time, that's one way to show a linear relationship. Okay? Table C, on the other hand, 1, 2, 3, 4, 5, 6, 7 was 1. Where's that? That's 8. So what's 1/8 of that? I don't know. Down there. 2 was 2. Double 1. 3 was 4. Half of 8. 4 was 8. 5 was 16. Okay, now we're making progress. 6 was 32. 7 was 64. Does that look linear? No. We are doubling. We're not going up by a consistent amount. We're not adding by a consistent amount. If you want to graph that thing, makes a nice curve. It's definitely a pattern, but it's not linear. Okay? So, last thing, a little more English. Circle the correct alternative. A sequence in which the next term is determined by adding a constant is called, is that arithmetic or geometric? Tanner? Huh? Hello? Is that arithmetic or geometric? Well, flip a page back. Yeah, it says it, okay? And if you can add a constant to the previous term and you graph it, does that make it linear or nonlinear? Linear. Okay? Just finished saying that. Conversely, if it's multiplying, we call that geometric. And this is not a linear function. Okay? So, is this pretty straightforward for our first lesson in sequences and series? Enjoy it, because it will get tricky. Okay? Don't think of this as a joke. Like, seriously, it will help as we go on. Because I'll ask you in a few weeks something that basic, and you'll just be, I don't know. If you don't know that, how do you know which formula to use? Look on your first page of your book. See all those formulas there? All the ones in the top, those are all for sequences and series. Does those look kind of confusing? Okay? So, like I said, enjoy this while you can. 1 to 12, and if you're really keen, if you like math puzzles and games, have a look at 13 to 15.